Okay, so just when you get comfortable with double integrals, we now go to triple integrals. All right, so let's guess for a moment. Let's think about this. We had the area was the double integral over a region, dA. So that gave us area as a double integral. And then we could write that as A is equal to the double integral over our region. Okay, wait a minute. How much did we do in the polar coordinates? Let me see. Okay, I guess we're all right. Nobody asked any questions, so I'm gonna keep going. Okay. So this was dx, dy dx, or dx dy. And then we said this could also equal the double integral over the region of r dr d theta. So that gave us area integrals. So then we went on to say, well, if we have a function floating over top, then we can do the volume. And the volume is the double integral, again, over the region of the function f of xy dA. So that means that we could say the volume is the double integral over the region of f of xy dy dx, and that's also the double integral over the region f of r cosine theta, r sine theta, r dr d theta. So if f of xy is actually a density function, then we can calculate mass. So mass is the double integral over the region rho of xy dA is mass. So that means that we're going to now have, I'm going to define this piece right here. Whoa. To be dm. So that implies then that the mass is the double integral over the region dm. Okay, so now we have some item floating over top of some function, and I'm now applying a density. So now I'm not looking at a function floating over top of a region. Now I'm just talking about what's going on with this particular region itself. So let's say I have this, and then in the XY plane, I have what we call, this is a lamina or a flat region that has a density to it. Okay, so I'm gonna look at the center of this. Okay, so this is some point XY. All right, so we can talk about the polar moment of inertia I of the lamina R about the z-axis. So we're going to define that. I0 going to be the double integral over R. Now, if you remember when we talked about this before, it was, we looked at the distance that it was from the mass, okay? And so if this distance is R, this is going to be R squared times whatever your density is, times your area. So this says then that I naught is the double integral over the region of x squared plus y squared rho of xy dy dx. Or if I want to write it in polar coordinates, the integral over r. We already had r squared. We have to write rho as r cosine theta, r sine theta, and dy dx then becomes r dr d theta. Okay, so that is the polar moment of inertia. And let's talk about the coordinates of center of mass. Okay, well, if you remember from before, in order to find the moment about the x-axis, well, the moment about the y-axis, we have to look at the distance it is from the y-axis, and that was x. And then we divided that by the mass. So the x coordinate of the moment of inertia is 1 over the mass, the double integral over the region. This was my. And then we have to multiply by dm, which is dA. And then the y coordinate, 1 over m. And now we have to multiply by mx. And mx, we need the distance y from the x-axis, dA. Okay, so we can define all of that stuff in terms of a double integral. Okay. So we can look at mass in terms of density dA. Okay. Now let's move to some more stuff in 3 dimensions. So say we have a rectangular block. Okay, so X is going to go between A and B, and Y is going to go between C and D. And then Z is going to go between P and Q. So I'm going to take my rectangular block. So here's a rectangular block. And so it's a very small rectangular block, very, 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 very small. So its volume is simply the change in X times the change in Y times the change in Z. So now, where this is a smaller block, that is inside. So this is a smaller block here. Okay. So I'm going to make a partition P into T1, T2, all the way up to Tn. And this is a partition of smaller blocks. And then as we do, we're going to make a selection, which is going to be some small point. Let me blow it up for a minute. So we're going to take a selection. And this is going to be a bunch of xk star, yk star, zk star so that's a select point for each block. Okay. Then if I have a function, let's say it looks like maybe density or any other function. So I can look at the sum k equal 1 to n f at xk star, yk star, zk star. And then I'm going to multiply by delta v. So now I get a triple integral and that is the integral, the triple integral over t. So that is over this whole thing. So let me just go back and call this whole thing t. Just like we had a region in the ground, now we're going to have t is a region in 3 space of f of x, y, z, dv. This is the limit as n goes to infinity of the sum of k equals 1 to n of f of xk star, yk star, zk star. And this becomes, oh, okay. So for example, we want to evaluate the triple integral over t of x, y, the sine of yz dv. T is the parallelepiped bounded by the planes x equals pi, x equals 0, x equals pi, y equals 0, y equal pi over 2, z equals 0, z equal to pi over 3. Okay, so that actually just looks just like what I've already drawn. Okay, we get the idea. Okay. All right, so that's what we have. So we want to compute that integral. So we're going to get the double integral. This one is an easy one because all of the limits are constants. So this says that this is going to be xy, the sine of yz, and dz, dy, dx. So z is going to go from 0 to pi over 3. And then y goes from 0 to pi over 2. And x goes from 0 to pi. Now, as you can see, I can't pull anything out, but I can integrate this in any order that I want. Okay, since these are all constants. Order doesn't matter.
You can't pull the x out.
You can pull the x out. That I can do. I can pull the x out. I definitely don't want to integrate with respect to y first because I would have an integration by parts. So I'll make a note to myself. If I integrate with respect to y first, I'm going to have an integration by parts. And we don't particularly care to have to do that unless we want to. So yes, Marcellus, you are correct. We can pull out the x. Okay. So then when I integrate with respect to z first, well, how wonderful is that? The y disappears. So I just end up with minus cosine of yz evaluated between 0 and pi over 3 dy. Well, this integral turns out to be pi squared over 2. So that part was easy. And then now I need to put in what happens when I put in pi over 3. So this is going to give me the integral from 0 to pi over 2. When I put in 0, I'm going to get 1. And then when I put in pi over 3, I'm going to get the cosine of pi over 3y. dy. So now I'm going to get y minus 3 over pi, the sine of pi over 3y, evaluated between 0 and pi over 2. So I have pi over 4 and then I'm going to have times pi over 2 minus 3 over pi times the sine of pi squared over 6. And that's a value. Oh, this is a 2. Okay, now it's right. Something's missing. Oh, I just made it look nicer in my notes. I just made it look like pi over 4 times pi squared minus 6, the sine of pi squared over 6. Okay. All right, any questions about that? All right, so let's do some applications. All right, so if you integrate, so if you know the volume is the triple integral over T dV, then that means mass is going to be the triple integral over T of density times that. So now we can talk about mass. And of course, once we start talking about mass, we can talk about centroids. So you can talk about centroids of three-dimensional regions. Okay. So the x-coordinate of the centroid is going to be 1 over the mass, the triple integral, and this is x, the density, dv, y, 1 over the mass, triple integral of the region of y times rho of x, y, z, dv, and z is the triple integral over the region of z times rho of x, y, and z, dv. And so now we can define the moments of inertia about the three coordinate axes. And these are as follows. Ix is the triple integral, apologies, of y squared plus z squared times the density dv. So you can see these integrals can get pretty thick. So this is going to be x squared plus z squared x squared plus y squared Okay, any questions about having to compute any of those integrals? So if you're asked to find those, that's what you do. Okay. So let's look at triple integrals of z simple regions. Okay. So this region is going to be Z simple. The reason why it's going to be Z simple is because this is going to be Z2 of X and Y. And then down here, this is going to be Z1 of X and Y. And then there's some region R that is the projection down onto the XY plane that this thing is over top of. And so now we can see that Z is going to start on the bottom curve and go up to the top curve. So here, Z1 of XY is less than or equal to Z is less than or equal to Z2 of XY. And then you have to figure out your region R separately as if you were only just doing R. So now the triple integral over T of a function of X, Y, Z dV now becomes the double integral over the region. And now I'm going to do the integral from Z1 of XY to Z2 of XY F of XYZ dz. Now, you will see that this is equivalent to what we were doing before. Okay, because what we were doing before, if I integrate the dz first, if I'm just trying to find the volume, if f of xyz is 1, this is a very easy integral. Okay, so now I want to project T into R in the XY plane. All right. So let's say my region is vertically simple in R. So if it's vertically simple in R, well, that's y2 of x. And this down here is y1 of x. Then I know that if I fix an x y is going to start at the bottom curve and go to the top curve. So I'm going to get y1 of x is less than or equal to y is less than or equal to y2 of x. And then x is between some a and b. Then I would end up with the double integral over t of f of x, y, z dv. Well, x is going to go from a to b. Y is going to go from y1 of x to y2 of x. So that's my integral over r. And then z is going to go from z1 of xy to z2 of xy. My function f of x, y, and z. And then I'm going to get dz, dy, dx. So that is a z simple region. Now, you know, if there's a z simple region, there's also an x simple and a y simple, so everything can turn sideways. All right. So if the region is x simple, then your double integral over t of f of x, y, z dv will be the double integral over your region R. Then you're going to have the integral from x1 of x of yz to x2 of yz, your function f of x, y, and z dx. dA. And here, R is in the YZ plane. And dA is either dz dy or dy dz. Okay. In the last 4 minutes, I'll define y simple. And then we'll pick up here tomorrow. So let me go back here and write x1 of yz is less than or equal to x is less than or equal to x2 yz. So this is now going to be y1 of xz going to be less than or equal to y, which is less than or equal to y2 of yz. So I'm going to get the double integral over t of f of x, y, z dv. It's going to be double integral over r f up times the integral y1 of xz to y2 of xz f of x, y, z dy dA. And here, r is in the xz plane, and dA is dz dx, or dx dz. So, any questions? Let me see who's here.
So if it's y simple, then it's also x and z simple, and same for the others.
No, it can be one or some things may be X, Y, and Z simple, but most things will only have one, most things will only have one direction that they're simple.
Okay.
So it's either going to be, it can be all three simple, like a sphere would be all three simple.
Oh.
But most things will look like this picture right here
And that's only
is Z simple. If it was turned on its side,
it will be y or x simple.
exactly.
Okay.
Exactly.
I get it now.
Okay. All right.